First of all, I'd like to thank the organizers for making this event possible and also giving me the opportunity to speak here. And I would also like to thank Peter and Samuele for designing this extremely interesting semester, and also for your efforts and generosity in, both at the scientific level but also the human level for creating this very welcoming atmosphere. Thank you. So yeah, my talk has the title of Endomorphism. Algebras of geometrically split genus to Jacobians over Q. And it is a follow-up talk of Chevy's talk. So there's this saying that second halves were never good, but I hope it will not apply today. But let me take it exactly where Chevy left it. So theorem 1. Maybe let me introduce first some notations. So I'll denote by D1 the set of absolute values of discriminants of quadratic imaginary fields with trivial class groups. And then I will also use the notation D2 for the same thing, but now I take quadratic imaginary fields with class group Z mod 2. And then I will also use the notation D22 for absolute values of discriminants of quadratic imaginary fields with class group isomorphic to Z mod 2 cross Z mod 2. Remember that these quadratic imaginary fields played a very important role in Chevy's talk. And so Chevy, let me recall what he proved. So he showed us that if we have some abelian surface that is defined over Q and that is geometrically split, so such that so that base change to Q bar, it is isogenous to the product of two elliptic curves, E1, E2, which are defined over Q bar 2. Then there is a finite number of possibilities for the geometric endomorphism algebra of A, and he described them. And so these are these possibilities. So then the geometric endomorphism algebra of A, base change to Q bar. So the ring of endomorphisms tensored with Q is one of the following. So I'm going to organize these possibilities in 3 cases for convenience for this talk. And these possibilities were, so I'll put in the first case the possibilities Q times Q, or M2 of Q, and Q times a quadratic imaginary field of class number 1. So it's something of this form where D is in D1, okay? Then in the second case, I will put products of quadratic imaginary fields of class number 1, which are distinct, so things like this. where this D1 is distinct from D2, and they both belong to D1. And then the third case, which was the most interesting case in Chevy's talk, was when we had a 2x2 matrices with entries in some quadratic imaginary field, but now this quadratic imaginary field could have so trivial class number or class number 2, or the class group was allowed to be Z mod 2 cross Z mod 2, except that 6 discriminants were forbidden, right? So let me maybe write this set with a subindex S. This means so some subset in here in which, so I was Chevy was excluding the discriminants. Let me see. 195, 312, 340, 555, 715, and 760. Okay? So in today's talk, what I want to do is to look at the problem of which subset of endomorphism algebras will occur when we restrict to Jacobians. Okay? So that will be theorem 2, which was obtained together with Chevy, but now Enrique Florit also joined the endeavor. And actually, I should say that we are thankful for many people who helped us to prove this theorem. And oops. Yeah, and I should mention several names, but at least I should mention that. So we were assisted by Noam Elkis and Fabian Narbonne and Christoph Ritzenhaller. So I will explain their contributions as long as the talk goes on. I'll also mention contributions by other people, but at least these 3 names have to be here. And so what we do now is we look at some curve of genus 2 defined over Q, whose Jacobian is geometrically split. So now when base change to Q bar, its Jacobian is the product of 2 elliptic curves, E1 and E2. Okay, both defined over Q bar in principle. And now the theorem will tell us what's the set of possibilities for the geometric endomorphism algebra of the Jacobian. So then this endomorphism algebra is one of the following. And okay, we'll have 3 cases again, but just to keep you thrilled, I will not complete the theorem, the statement of the theorem now. We will do it along the talk proceeds. And the talk will have 3 parts, and in each part I will explain which of the algebras in each of these 3 types can be realized by Jacobians. So let me start with the first part. So I'll look at this. At this case, and this case is really easy, and everything boils down to some basic construction that I want to explain you. So first part is the basic construction. so we look at this genus 2 curve, y squared equals x to the 6 plus ax squared plus b, where a and b are some rational numbers. And then this curve has obviously a morphism to the elliptic curve that I'll call E1, y squared equals x cubed plus ax plus b. That sends some point xy to the point x squared comma y. Right? That's quite obvious. It's almost as obvious that it has a morphism to some other elliptic curve, E2, that has the equation y squared equals, now I multiply by x. And now the morphism is sending a point xy to a point x squared again, but now I plug here xy, so that when I raise this to the square, this x will be cancelled. Okay, and let me call this morphism phi, this morphism he, and this curve has some automorphisms. So on this side, I have an automorphism sigma that sends the point xy to the point minus xy, and it has an automorphism tau that sends a point xy to the point minus x minus y. And the connection of these automorphisms with these morphisms is that if I now take the pullback of E1 by the morphism phi, then it's easy to see that this elliptic curve is fixed by this automorphism. And similarly, the pullback by he of E2 is fixed by tau. And now these two facts, together with the fact that sigma and the composition of sigma and tau is minus the identity, tells me that these two elliptic curves cannot have much in common. And so they can only intersect at two torsion points, which means that their sum together must generate the Jacobian of C. In other words, if I consider the map, the product map of the pullback by phi and the pullback by he from E1 to E2, then I get an isogeny to the Jacobian of C, which is what I wanted. A way to realize products of elliptic curves as Jacobians. And the remark here is that with this very easy construction, you can realize all algebras of type 1. So with this construction. So yeah, the first case is what you will generically find. Now to realize M2 of Q, you have to make sure that these two elliptic curves will be isogynous. But in fact, if you put here some, if you can work out that these two curves will be in fact, in some cases you can even make them isomorphic and then realize M2 of Q. And then to realize the product of Q with some quadratic imaginary field, well, it's a computation. You put some curve with Cm that you like, and then you just check that the corresponding other curve doesn't have Cm. Okay, so with this, you deal with the first case. So far, not much has happened, because here we just have the same algebras. the interesting stuff is happening now. So now let's look at type 2. Yeah, or maybe, is there any question so far? No? Okay, so for type 2, I start with some remark. So, which is that, so in this previous construction, the two elliptic curves have the isomorphic two torsion as GQ modules. And now you could ask, well, is it the case that whenever I have isomorphic two torsion, can I build a Jacobian out of two elliptic curves? And well, not always, and there's some subtlety, but there's a theorem of Canny that tells you when you can do it. So let me state the theorem by Canny. So, yeah, let E1 and E2 be elliptic curves. Defined over Q. Canny's theorem is much more general, but we will just need it over Q. With the property that there exists some isomorphism between their two torsion. And then he adds the hypothesis, which does not come from an isomorphism of the elliptic curves themselves. So, in that case, you can find a Jacobian you can find a genus 2 curve whose Jacobian is isogenous to the product of these two elliptic curves. So then you can solve the problem. Okay. So this gives you somehow more freedom. You don't need to restrict to those specific models. And then, yeah, that's what we try to exploit with one remark that, so this is an existence theorem, but there's a very constructive version of this theorem, which is due to Howe, Lever-Prost, and Poonen. So they give some constructive version of it. Okay, so now we want to realize products of quadratic imaginary fields with class number 1. That's the case that corresponds to elliptic curves which with CM but non-geometrically isogenous. So we looked into the LMFDB for such curves of this type that will have isomorphic two torsion, and we found the following. So let me give you some examples of CM elliptic curves with the isomorphic two torsion subgroups. And we found 3 pairs. So we found one pair, E1, E2, E1 having Cm by q square root of minus 4, and E2 having Cm by q square root of minus 3. We also found another pair. This time the Cm was by square root of minus 4 and square root of minus 7. And finally, we had 1/3 pair in which the Cm was by square root of minus 4 and square root of minus 8. Okay, and maybe, yeah, I can give you the LMFDB levels of these curves. Just to emphasize that if you are looking at this problem, you can just go into the LMFDB and search for these. So this is 144A3. Oops, okay. Maybe let me put here a 3, here a 4. And these two have conductor 256. Okay, so we had these examples that we could realize by Jacobians by using this constructive form of Canny's theorem. And now my claim is that you cannot find anything else. So in here, you just find algebras of this form. Where the pair D1, D2 is one of those three. So 4, 3, 7, 4, and 8, 4. Okay, so now let me explain it to you how one can try to prove this. Yeah, is there some question so far? Okay, so
For these three examples, what are the two torsions?
sorry?
What's the Galois actions of these three torsions?
So I don't know it off the top of my head, but you can just go to the LMFDB and it is there. Mm-hmm. And okay, now so we have this existence theorem, this constructive theorem. In order to forbid some possibilities, we need some kind of forbidding theorem. It is supplied again by Canny, together with Frey. So let me explain to you. So now suppose you have now some Jacobian which is isogynous to the product of two elliptic curves. Now these elliptic curves are over the field of definition of this Jacobian, so over Q. Then Frey and Canny show that in this situation, there always exists some number, at least some integer number, at least 2, and elliptic curves I'm going to call them E prime, E sub I prime, isogynous to our originally given elliptic curves, such that the n torsion of these elliptic curves are, these n torsion subgroups are isomorphic as GQ modules. So So if we want to prove that theorem, all we have to do is that for each of the pairs that do not show up in there, it is impossible to have isomorphic n-torsion subgroups for the elliptic curves with CM by those pairs. And okay, that's, let me give you the idea of how we solve this problem. It was by means of the following proposition. So now at this point you have to look at all possible n's. This proposition will tell us you only have to look at certain n's. And it goes like this. So the hypotheses are the same. So we have some genus 2 curve defined over Q, whose Jacobian is isogenous to the product of two elliptic curves defined over Q. But now I assume that these are CM elliptic curves. And I call the CM field M sub I. Then suppose that we can find the following. So, well, first there's some technical assumption. First exclude the case in which one of the fields is q square root of -3 or q square root of -4. You'll see when I give the sketch of the proof why we are excluding this. And then suppose that there exists some prime with the following two properties. The first property is that it is inert in M2, in one of the CM fields. The second property is that it splits in M1. And assume also that its trace is non-zero. So with trace from M1 to Q, this is non-zero. Then my claim is that if the n-torsion subgroups of E1 and E2 are isomorphic, is this visible? Oops. Then it must happen that this n is a divisor of this trace. So, okay. Oops. So first of all, how can this proposition help in our problem? Well, what you do is you look at pairs which are not in here, and you always find one such prime. And once you found one such prime, this makes you just have to check that a finite number, because this bounds your n, of n-torsion groups cannot be isomorphic. And this you deal it by computation, case by case. You look at the n-torsion fields of CM elliptic curves are very well understood, and you just check that this finite number of cases is not possible. So the proposition, together with the theorem, turns this case into a computation. Let me explain you the idea of proof of the proposition. So let me, yes.
If I repeat this with different times, I assume I can pattern those, it gives you different bounds. So if you combine those for many p-naughts, I assume you get something very small. But there are cases where you don't get one, so you really have to
Yeah, there are cases where, I mean, we were always finding something that was a multiple of, and we didn't prove that it always had to be a multiple, but in practice we saw it, and it was just easier to check that.
Just to understand how large can this common multiple be?
Yeah, I think they were fairly small, like it was 2 or 3, maybe in some case 6, but and of course we would choose different p naughts, right, to get the smallest possible bound. Yeah, yeah, good point. So the idea of the proof. Let me first write something that does not quite make sense, but then I'll explain you how to fix it. So we have that the n torsion of E1 and E2 are isomorphic. So if I look at the Frobenius trace of E1, so that's Frobenius trace, then this has to be congruent with the Frobenius trace of E2 at the same prime P naught, modulo n. But now I have that this prime P naught is inert in M2, and we know what this means for CM elliptic curves. It means that this Frobenius trace has to be 0. And then it's an exercise in Silberman, so it is the exercise that if the prime is split, then this trace will be given by the appropriate choice of P naught, and then taking the trace. So here we get plus minus the trace of P naught from M1 down to Q. I'm writing plus minus the trace because this P naught is not quite uniquely defined. It depends on the units you have in M1. That's why we are excluding these cases, but we're happy to exclude those cases because those cases actually, they do occur, right? We don't want to exclude that case that we know it occurs. And yeah, so you have this ambiguity of the sign, but then it's not a problem. This already tells you that n has to divide this trace. So why this argument is not completely right? Well, it could be that our elliptic curves have bad reduction at this prime P naught, and then we cannot use this prime. And in fact, we are allowing these elliptic curves so much freedom. We can take any quadratic twist that they can have bad reduction at any prime, but they cannot have bad reduction at all primes, and or at infinitely many primes, and that's the key. You realize when you make this argument that pi naught is in fact characterized by congruence conditions in M1. And then you can apply the analog of Dirichlet's theorem of primes in arithmetic progressions for quadratic fields to obtain an infinite supply of primes P naught, and therefore of primes, so of primes pi naught and then of primes P naught. So and then, yeah, then you do the argument. It's going to work for some of those primes. Yeah. So, and yeah, are there any questions about this? How one proves the theorem in this second case? That's the general idea. Then there are lots of it's an easy exercise by looking at these n torsion fields and checking that this finite number of possibilities that the combination of the theorem and proposition leave are not possible. Okay, so let me put this on top. So we are just left with the the third type, the most interesting one, so let me explain to you what goes into the proof of this case. So first of all, this type is sort of divided into 3 subtypes. Let's look at type 3. So the first subtype is the case in which you're so now we're dealing with the case of elliptic curves which are geometrically isogenoous to the square of a CM elliptic curve, and the CM field has either trivial class group or class group isomorphic to Z mod 2 or class group isomorphic to Z mod 2 cross Z mod 2. When you have trivial class group, then there are curves in the literature realizing each of the 9 algebras. So curves appear in the literature. And so you can find all of them. So not all of them are in a single reference, but they're all in the combination of Cardona's thesis and the work of Jalan, Howe, and Rittenhaller. Okay, so yeah, I won't say more about this. And then you have the case in which the class group is Z mod 2. And in that case, there were already some algebras that we couldn't realize by curves in the literature. What you do in this case is you go back to the theorem of Canny, and you try to glue elliptic curves along the 2 torsion. Which elliptic curves? Well, in that case, you can define your elliptic curve over a quadratic field because the class number is 2. And then you can consider its Galois conjugate, and you can glue them along 2 torsion. And that's how we handled that case. And so this leaves us in this final case in which our quadratic imaginary field has a class group Z mod 2 cross Z mod 2. In that case, such an approach is not really possible because now your elliptic curve is defined over a quartic field. It was really surprising to us, in fact, that in that case you would actually find jacobians. But it was not surprising to Noah Melkis because he gave us lots of examples. So in fact, maybe let me write the answer here. So in this case, we have M2 Q of square root of minus D, where this D belongs to D1 union D2 union those D comma D2 comma 2 that occur for surfaces, except that there will be 5 discriminants that will be forbidden. So in that case, you have to exclude these 5 discriminants. Let me check them. Sorry? So we have to exclude more. We have to exclude 5 more. Maybe did I say it?
More than half of the things in D2 too?
You mean if I'll give you the numbers now then. So let me first write this. Oops, sorry. You exclude 280, 483, 595, 627, 795. So numbers. There are 24 in here. You exclude 6 here, you get 18. And now maybe let me call that set the set of discriminants that occur for Jacobians D2 comma J. Then this set has cardinality 13. And then, so for all, for all D in this set that we ended up seeing that occur among Jacobians, except of 2, I think it's 10, 12, 14, 35. Noah Melkis. Sent us curves. Okay, and then, and at that point, we didn't know what was happening with the 5 remaining discriminants, neither what was happening with these 2 other discriminants. And we were stuck in there for quite a long time. But what we were thinking, okay, maybe there's nothing else. Let's try to rule out these 7 remaining discriminants. So how would you rule out these discriminants? And well, we thought, well, let's try to understand our situation closely. So let's suppose that there exists some genus 2 curve with Jacobian geometrically isogenous to the square of an elliptic curve where this elliptic curve has Cm by some D in this set D to okay, we know there must exist. So if a Jacobian exists, there better exist some surface, so we can already assume it belongs in here. And then what we did, so we realized that from our previous work with Chevy, which actually was explained in detail in his talk. So from Chevy's talk, you find that this situation will in fact only occur if your Jacobian is in fact isogenous to the product of an elliptic curve over the Hilbert class field. Cm by this field, where this D is in here. So this will only happen if in fact it already happens over the Hilbert class field. And your elliptic curve is in fact a gross Q curve. And then once you have this, that's very useful because then you can, by looking at ring class number formulas, in fact you see that this elliptic curve does not just have Cm by some order in this field, must have Cm by the maximal order. And when you have this, then we use the work of Keaton, so Jordan, Keaton, Poonen, Rains, Shepard, Barron, and Tate, to show that in that case, in fact, your Jacobian has to be isomorphic to the product of 2 elliptic curves with Cm by the maximal order. So there are three crucial reduction steps in here. First, we go down from Q bar to the Hilbert class field. Then we go down from Cm by any order to Cm by the maximal order. And then we show that it's not just isogeny, it has to be isomorphic to a product. And then, well, the first thing we did was, well, let's see if Elke's examples have this property. And I should thank Jeroen Sijsling for applying the code of your algorithm with Edgar Costa and John Voigt and Mascot to certify that all the curves that Noam Elke sent to us actually had this property. But beyond this, we didn't know much what to do until, Fabian Narbonne's thesis arrived. Which was the key to solve the problem. So let me quickly explain to you one of the main theorems in Fabian's thesis. So he shows that there is an equivalence of categories between jacobians defined over Q bar, which are isomorphic to the product of two elliptic curves with Cm by the maximal order. With the category of rank 2 OM modules, okay, with certain properties, which are like Hermitian, and I don't have much time to explain this, unimodular, and indecomposable, so that they give rise to Jacobians. And moreover, he is able to understand what it means for the Jacobian to have field of moduli Q in terms of the OL module. So let's say with field of moduli Q. And yeah, here also, let me write with field of moduli Q. And he does not only prove this equivalence of categories, he can enumerate things on this side. So he can compute the elements in this finite set. And well, our reduction left us in a situation very close to this situation, except that we want to have field of definition Q. And here, we only have, for the moment, field of moduli Q. So the way to address this was the following. So then it came, we have this finite set, and then it came Christophe. So I'm going to write your surname for the third time in this talk. And with the theory of theta constants, he can compute heuristic models for the corresponding curves. And once you have some the heuristic curve reconstruction, then you have a heuristic way to find what's the field of definition. And then you want to make sure that these computations are correct, and you can do it. So there are several ways. You can again use the work of Jeroen with Jean and Mascot and Costa, but you can also apply Kumar. That's what we did to certify correctness. So yeah, and using this technology, we could not only see that for these 5 discriminants, there won't be any curve defined over Q. They could also construct curves for these discriminants 10, 12, 14, 35. And I think it's my time to stop. I'd like to thank you for your attention.
Questions?
It's a comment, not a question. In the class number 2 case that you didn't spend very time on, you can find a construction for that case in a paper I wrote in 1992.
Okay.
I think.
Yeah. Yes. Yeah. So I should apologize for all the.
No, it's okay.
It's a problem that has looked many people, and yeah, there's a vast literature. And
it's the paper where I list all the imaginary quadratic orders of class number 2, but I left one out because I made a mistake. So, well, it's on page 7. I'll show it to you later.
Yeah, thanks so much. Yeah.
Are there other questions or comments? All right, well, if not, let's thank Francesc again.